about the image processing model, which is this part over here. Okay, so any operation, any image processing operation, it can be said to be some black box operation P, wherein we give the input image f of x comma y, and we get the output image as g of x comma y. Now, this same model can also be applied for image restoration and all, wherein we already have a corrupted image, some image with some errors in it, and that will be just directly g of x comma y. That will be the image that we get will be considered as the output image after some process p, which we don't know what it is. Okay, so that will come to that at a later point. Now, any image processing system will have two main properties. One is a linear system. That is, if I have two images f of f1 of x comma y and f2 x comma y, and its corresponding output image will be g1 x comma y and g2 x comma y, both of which are result of this operation p on f1 x comma y and f2 x comma y respectively. Then this p operation, or this model, the system which will create on this, which will be working on this process p, that system p is said to be a linear system if it satisfies this equation. Okay, that is, if I apply some constant a to the first image, alpha to the first image and beta to the second image, and to this both these images I apply this operation p, then the output is such that this constant alpha will be applied to the output of this operation p on f1 of x comma y, and beta will be on the output of operation p on f2 of x comma y. So if this system satisfies this property, then it is said to be a linear system. Now we also have something called as linear shift invariant system, okay, which is a combination of linear system and a shift invariant system. So if we have a shift invariant system, what it basically means is that if we apply any kind of shift operation on your image, input image, the same shift will also be applicable in the output image. Okay, so even though if there is a shift, that same shift will be applied in the output image. And linear shift invariant system is basically like a combination of both. If it is shift invariant as well as a linear system, then it can be said to be a linear shift invariant system. Now, if it is a linear shift invariant system, then it is considered to be it is considered as a convolution between the input image with some impulse response function. Okay, now this term impulse response function basically is given any particular value, there is a chance that it might be it's something like your what do you call that, Gaussian function, that is a bell-shaped curve, but the impulse is mainly just some very at some points it will be very high value, whereas the rest of the values corresponding x, the corresponding value to the input, will be very low. Okay, so this impulse response function we can also say is something like what would be the response if the input sensor is affected by some sort of light. Okay, so when we are considering the output image that is generated by a camera, the input to this would be your light which is falling onto that sensor, the part of that sensor, the sensor array that you have in a camera. Okay, and this h would be how that sensor, the h of x comma y, would basically be how the sensor is going to respond to certain amounts of light. Okay, so this h of x comma y, we can just consider as an impulse response function, and the output of this image is basically the convolution of this impulse function with the input image that we have. Now, this input image in terms of a camera, we can't directly have access to that because that is just your electromagnetic radiation. Okay, so what we get is a representation of this as an output of the convolution between the impulse response of that sensor with the light which is falling onto it. Okay, then so because convolution operation is a bit difficult and it is very computationally intensive, what we do is we apply Fourier transform to this operation. And if you remember, one of the properties of Fourier transform is if we shift it into a particular convolution operation into the frequency domain, then that convolution operation actually becomes a product operator. It's the same as calculating the product in the frequency domain. Okay, so this same equation g of m comma n as a convolution of h of m comma n with f of m comma n can be written as g of u comma v as a product of h of u comma v and f of u comma v. Wait, why did I put this? I think I was explaining something for it. Okay. Right. Image smoothing. I don't know why I put it before. If you can see this image, basically what is happening is at these points, in the left hand side image, you can see some rough edges over here. Basically almost every edge that is there come with black color. All of those edges are a bit rough. You have some errors coming into the picture. Okay, it is not smooth curves. You have some jagged lines coming. Okay, so in order to solve this problem, what we do is we apply smoothing operation. So if you see in this, it is not as prominent, but what is happening, we are also losing the details. So there is no, if I look into this particular area, then it doesn't show that clear separation between green and black. And even here, it doesn't show a proper separation between the white and the black. Okay, so this is the disadvantage of smoothing. Even though it does remove errors, we can have a loss of details in terms of the sharp edges that are there. Okay, so your image smoothing operation basically tries to remove this noise by usually taking an average of all the neighboring pixels. Now there are different methods where you can change this, but you still consider what are the neighboring pixels values to decide what will be the current pixels value. Okay, so the main reason why image smoothing is used is to remove this noise. Now, noise can be introduced in your image at the time of transmission. That is when you're sending the image from one location to the other, maybe over the network, there are some errors introduced in this. So you can have noise introduced in your image during the transmission. Another thing is during the capturing process. Okay, when you are capturing a particular image, let's say one of those sensors in your sensor array of your camera is damaged or it has some dust particles on it, it will not create a correct response that it should. Okay, so when this image is being created by your by the camera, it may have a wrong information at that particular point. Okay, so that is also another scenario where noise may be introduced. So what we do is we consider replacing a certain pixel which we feel is having the wrong value. That pixel's brightness level is calculated based on its surrounding pixels. Now, when I say surrounding, it may, if it is, let's say, what we usually do is we consider a 3 by 3 matrix, and we keep the noisy pixel over here in the center, and the surrounding pixels will then be either this, 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 and this. I think you'll have studied this in computer graphics, in which you had the 4 neighbors and you also had 8 neighbors. So if I have to consider only 4 neighbors, then these will be the ones. And if it is 8 neighbors, then along with those 4 neighbors, I have these additional 4 neighbors to be considered. Okay, so depending on the values of either the 4 neighbors or the 8 neighbors, I will be recalculating what will be the intensity value of this central pixel based on either a normal average. I'll just be taking the average of all the pixels, or I take the weighted average. Now, there are situations where you can directly take the average, or you will have to rely on taking a weighted average, because you can't, you don't want to lose. It is like, what do you say? You're trying to balance out either smoothing out, that is removing all the errors, or preserving the details, that is the edges that are there. So you'll have to keep in mind how exactly you will be calculating this. So you have to balance it out. So if you end up smoothing too much, you will be losing a lot of details. And if you want to preserve details, you may end up with a lot of noise that is left after smoothing. Okay. So depending on the situation, we will have to decide what exactly is this weights that we are assigning to each of the neighbors. Okay. Now, you don't have to come up with your own weights for this. There are already methods that are defined, and we'll see each of these. Now, whenever we do a smoothing operation, we basically have two major categories of this. One is in the spatial domain, and the second being in the frequency domain. So in the spatial domain, we basically get like that numerical we had solved, in which we had the 1/8 as the 8 neighbors weights. Okay, and in frequency domain, we shift the entire image into the frequency domain, and in that we then apply frequency filters. Okay, either you will have a high pass filter or a low pass filter, depending on exactly what you want to do. For smoothing operation, it will have to be a low pass filter. We are only allowing low frequency signals to pass through. Okay, so first thing we'll see is smoothing in the spatial domain. Now, the first method is basically your neighborhood averaging methods, which is basically taking the average of the 4 neighbors or the 8 neighbors. Now, in this, we can have either a 3 by 3 matrix or a 5 by 5 matrix. That is the number of pixels, the size of this matrix that we are considering, with the pixel whose value you want to calculate in the center. This is a 3 by 3 matrix. So 1, 2, 3, and 1, 2, and 3. Okay. Now you may have a 5 by 5 matrix wherein you have to consider not just those 8 neighbors, but you have to consider more than that. Okay. So in that case, your average, the weights will change. Now in the textbook, it only specifies these three, that is this, and this, and there are no mentions of 5 by 5 matrices. Okay, that is the convolution kernels that will be used. So if you're asked for neighborhood averaging, you can only draw these and say that if you want to increase the strength, basically how many pixels are getting affected to be considered when you're calculating the smoothing operation, you can use a 5 by 5 matrix or even a 7 by 7. Now this size will always have to be an odd by odd value, and preferably a symmetrical size. Okay, we can use matrices, the convolution kernels basically, with differing sizes, that is not necessarily a linear one, but that will depend on your application. If your application specifically requires you to use a non-symmetric convolution kernel. In that case only you can use it. But most of the times we prefer this. Okay. Now what we would have to do basically is we would just place this kernel onto the central, whichever pixel we want to calculate on that, with this 0 aligning with that pixel, and whichever values overlap with this, those values we consider as multiplied those values, and then we take the sum of all these products. Another more simpler way is just to consider the four neighbors of that pixel and take an average of that. So if I have an image, let's say, just consider a 4 by 3 image. Let's say 1, 2, 3, 4, 1, 1, 7, 5, 2, 2, 2, 2. Okay, and let's say that I want to calculate what is the basically the average of all of this using a 4 neighborhood averaging. That is this one. Okay, so if I want to calculate the average at this point, that is at 1 comma 1, then what I'll have to do is instead of placing this, taking this matrix and placing it over here and then checking which are the overlaps, I can just check which are the four neighbors. Okay, that will be this. Just a minute. The four neighbors of 1 comma 1 will be this, 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 and this. So I can just write it as 1/4 2 plus 1 plus 7 plus 2, and that is the same as applying the convolution with this, because the rest of the values as it is will be 0. Okay, so the sum of this 10, 12 by 4, that's 3. So I can, in my output image, I can replace this particular pixel at 1 comma 1 with the value of 3. So that forms like the average of the neighboring four neighbors that are there. Now we can also use the 8 neighborhood averaging method, in which I have to consider the 8 neighbors, all the 8 neighbors, not just the 4 neighbors. Okay, so in such a case, along with these 4, I'll also have to consider this, 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 and this. So my output will be basically the summation as 1 by 8, 1 plus 2 plus 3 plus 1 plus 7 plus 2 plus 2 plus 2. So that value which I get after dividing this by 8, that summation by 8, because these are 8 values. Okay, so I'm basically taking the average of all the surrounding pixels. Now we also have one method wherein we consider not just the 8 neighbors, but this current pixel also, that is this central pixel, and that is why these weights of all of this changes to 1 by 9. So it is like taking the sum of all these 9 pixels and taking their average. Okay, so individual pixels you would have to, since there are 9 of these, if I were to calculate what would be the weight of each, it would be 1 by 9, 1 by 9, 1 by 9, and so on. Okay, so depending on your operation, that is whether you want to consider just the 4 neighbors or the 8 neighbors or all the pixels in that 3 by 3 matrix, you can select any of these. Okay, it is just like taking the average of whichever pixels you're considering. Okay, now a slight variation to this is threshold averaging, wherein we consider the same concept as before, that is either using this matrix, that is either a 4 neighborhood or 8 neighborhood or all those pixels. Along with that, we also consider a threshold. Now, this threshold is like if this difference between the current value and the calculated value is greater than a threshold set, only then I can set this value as the new value of the output. Otherwise, it will stay as the original. Okay, so if this difference between the original pixel level, whatever is the gray level of that pixel, the difference between that with the newly calculated one after averaging, if it is more than the threshold, only then I will consider this new value that is calculated. Otherwise, in the output image, my output value is going to be the same as the input value. Okay, and Gaussian filtering basically is considering the Gaussian curve. Just if you have read about the Gaussian curve, it is basically a bell-shaped curve. And if you're using Gaussian filtering, you will have to make use of that Gaussian curve. So you'll be having something like, just a minute, I'll just erase this off and I'll show you all. So your filter basically is in this form. So you have very low values. It increases to a certain point at some place and then it decreases, and it doesn't exactly become zero at the other values. It becomes very close to zero. So as you go away from this central point over here, that is, let's say this is point A. So as you go away from this, your output value basically reduces and it nears zero. Okay, it doesn't become zero, it becomes very close to zero. So we are basically considering this as a filter, and since it is a we basically have to consider the neighbors. The output you looks something like this. I don't have the drawing, I think, of this. So if we were to have a Gaussian filter, something like this, you would have like this with the surrounding areas also coming like this. Okay, wait, I'll better show you all the image of the Gaussian filter. This part. Okay, so you'll be having in two-dimensional space, that is in just the input versus the output, you'll have something like this. But if you have to apply this Gaussian kernel across an image, what you'll have is this. So if we look at it from the top, the central pixel is the brightest. And as we go away from this central pixel across all the directions, the value keeps on decreasing. Okay, so if we were to view this in a three-dimensional form, that is, if we have the image basically across the XY plane and the value, the brightness level in the Z axis, then it would look something like this. Okay, now looking at that, I also remembered I was supposed to show you all that this thing in terms of the gray levels I was explaining. The differences between having a single gray level and multiple gray levels. It's not here. Right, this one. So you basically can tell this difference between this black and this gray, but as you go down, you cannot tell the differences between individual colors. Okay, so that is what I was trying to tell you all yesterday. Now, coming back to this, so we can use this Gaussian filtering. Now, depending on that equation, that is g of a will depend on e raised to exponent. It's basically an exponential equation. Okay, so as we go away from this central point, the value keeps on reducing. Okay, now till as of right now, Gaussian filtering has not been asked, because you would then have to calculate what is the value of the Gaussian filter at each coordinate. Okay, so that is the reason why Gaussian filter till now has not been asked, but it is not in terms of like that it cannot be asked. That is not the case. Okay, Now, the main thing that we usually go for in case of smoothing is either neighborhood averaging or median filtering. Now, median filtering is basically right. This is examples of Gaussian filtering, basically. Yeah, so you can see over here all of these spots which are coming here. This that is removed with smoothing. Let me just check if I have deployed with 3 by 3 kernel, and this is 5 by 5 kernel. Right, so this basically is removing something called as an impulse noise. In this specific case, it is called as a salt and pepper noise. We'll come to all of this. And applying filtering, you can see that all of those points are removed, but we are also losing the details. Okay, and then we are going to this. Okay, so coming to median filtering. Now, given a particular image, if we want to apply median filtering to it, what we need to do is we basically consider what are the values of that particular image, and depending on those values we have to calculate what is the median after sorting those values. So let's just consider an image 0 2 2 2. Okay, so let's just say this is my input image. Now, in median filtering, what we do is we'll first have to consider what are this particular pixels. Okay, the pixels that we want to consider. So the first one will always be 0, 0, and then we'll going one across the other. Now, in median filtering, what we need to do is if we are taking either 4 neighbors or 8 neighbors, usually we consider it as a 3 by 3 matrix. So we'll be considering all the values. So if I am using this particular value as for this particular pixel as a reference, I'll be considering all these 9 pixels. Okay. Now, this window for median filtering will basically decide how many pixels are to be considered. The minimum size for the window in case of median filtering is 3 by 3, and you can go higher than that also. You can use a 5 by 5 window or a 7 by 7 window also. But because we'll be needing to calculate the median, which is like the middle value in a list of values. Okay. Because of this, we prefer to take a odd by odd size when you're taking this window. Okay, so most of the times you will find median filtering the size of the window as 3 by 3, 5 by 5, 7 by 7, and so on. Now, in the case of boundary pixels, that is pixels which are over here, okay, even if I take a 3 by 3 window or a 5 by 5 window, in these cases, in all the images, okay, even if you take a 100 by 100 image also, this problem will arise. And the problem is that when I take these boundary pixels, I will always get an even number of values. For example, I'll show you. Let's just consider that I want to calculate the median. First, I'll give an example of this value, okay, at 2, 1. Okay, then I'll come back to each of these and then I'll explain why exactly that problem comes into picture. So first we'll see how exactly we have to calculate the median. So if I want to calculate the median at 2, 1, that is of value 6, and let's say I'm using a median window of 3 by 3 size. Okay, so I have to consider all of these pixels that is surrounding the pixel which I'm considering the value to be calculated. If I put a 3 by 3 matrix on it, centered at that pixel, which pixels are going to come inside that window? Okay, so all of these pixels which are inside that green will be coming under this 3 by 3 window. Now, to calculate the median, I'll have to write all of these numbers numbers and sorted. So I'll be having 2, 3, 5, 5, 5, 6, 6, 6, and 7. So this is my sorted list of all these 9 numbers. Okay. Now, from these 9 numbers, the median will be the fifth number. That is, this fifth number becomes the median because it has 4 values on its right and 4 values on its left. We're not calculating the average, we are calculating the median. Okay, so in this case, the output of this will be 5. Now, let's say I shift this. That is, I move this particular value from 2, 1 to 2, 2. This is 3, 3. Sorry, that is the value of that is 3 and this is 6. I'll just rub this off. So at 2, 1, sorry, 2, 1 is already calculated. At 2, I will have to consider these as the 9 pixels inside this window. Okay, so here the next median will be, after sorting the list, 3, 4, 5, 6, 6, 6, 7, 7, 7. So the median here will be 1, 2, 3, 4, and this value 6. So this value median will be 6. So the output image will be having 2, 2 as 6. Okay, so this is how we solve median filtering. Now, coming to the boundary pixels. That is, if I am calculating the median filtering for pixels anywhere in this particular range, I'll just mark all of those pixels. That is, if I have these pixels and these pixels. So anything inside these yellow, those are my boundary pixels. Okay, so I have this, 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 this. Basically, all of these other than 1, 1, 1, 2, 2, 1, 2, 2. All of these circled in yellow, since they are next to the edge of the image, we call these as boundary pixels. Okay, so let's just consider if I want to calculate the median filter at this particular point. Let's say this one. Okay, so in this case, the window is going to lie something like this, wherein I'm losing these 3 values. Okay, so in my window, median window, I will only have 6 values. So in this case, you have an even number of values, and therefore, after sorting it, there will be 2, 2, 4, 5, 6, 7. So in case of median of even number of elements, we basically consider 2 values. That is, these 2 values become the median. Okay, so I have 2 values on its left and 2 numbers on its right. So these 2 values become the median, and therefore the final median value is an average of this 4 and 5, which will be 4.5. So approximately 5. Okay, now this is one way. That is, you can just consider, you can shrink this window. Okay, that is, one method is to shrink the window. So instead of using a 3 by 3 in this case, we are actually getting only a 3 by 2 window for border pixels. Now, this is going to get even worse if I am considering this particular pixel to be calculated. In such a case, what will happen is the window will have to be shrunk to 2 by 2. And over here, in this case, the median will be average of 2 and 2. That will be 2. Now we'll solve this median filtering example in class because this gets a bit confusing. That is, this is one method, that is shrinking the window. Okay. There is another method which is basically ignoring boundary pixels, but that is only applicable in very large images, very large as in more than 100 pixels by 100 pixels. Okay, so the resolution would be 100 by 100. In such cases, you're not losing any data. For your paper, you will get images in terms of 4 by 4 or even 3 by 3. In such a case, you cannot, uh, what do you say, you cannot ignore the boundary pixels. Okay, so when you're applying median filtering in, let's say, on a computer, you'll be usually having images in terms of either 640 by 480 or larger than that. Okay, so in such cases, you can ignore boundary pixels, but in your numericals that you will get for paper, you cannot use this method. Okay, ignore boundary pixels is another method. So you cannot use this in your semester papers. The third basically has two ways. One is to wrap the image around. So if you have this, okay, the simpler one first, you can fill window with 0. So if I have, that is, if I have something like this, what I will do is instead of considering it as a 2 by 2 value, sorry, in this case, 2 by 3, instead of considering that, I will consider that these are 0, 0, 0. And when I calculate the median, it will be 0, 0, 0, 2, 2, 4, 5, 6, 7. So my median becomes this fifth value in this list, which is 2. And the second method is, instead of filling it with 0, what we do is we wrap this image around. That is, we consider the image to be a cylindrical way. Okay, not in terms of this. So what we do is, after this particular pixel at this point, we consider this 3 pixels to be the value. So if it was a circular image, that is, if we took this image as on a paper and we wrapped it around so that the edges meet, then instead of having 0, 0, 0, we would just copy the values on the leftmost side in this case. So we would get something like 0 to 5 over here. Okay, the same thing applies on the left hand side, top as well as bottom. So if you're using, considering it as a, what do you call, there's a term for it, just a minute. Connect, basically copy entries from other places. Or what you can do is, instead of considering it as circular, you can just copy this value. That is, from, if I need to fill this up, to fill this value, I can just take whatever value is the last value and copy that same thing into the right or the left portion. Okay. Now, another method, instead of just taking these values directly, is weighted median filtering, in which we apply weights to each element. Now, because we don't find out the average as such, what we do is we apply the number of times a particular value is repeated. So if I have a mated median filtering, the kernel as this 2, 1, 2, 1. Okay. What I will do is I will be repeating the pixel in the center thrice, over here twice, these four places, and this place it will be repeated only once. So if I had to find out the median filter with let's say the neighbors are something like 3, 5, 4, 6, 6, 7, 6, 7, 7, and I want to calculate what is the median of this particular pixel, then I just have to repeat after placing this kernel onto this particular image. I will be basically repeating 3 once because that is overlapping with this, 5 twice because that is overlapping with this, 4 once because that is the overlap, and so on. So I'll be getting something like 3, 5, 5, 4, 6, 6, 6, 6, 6, 7, 7, 6, 7, 7, and 7. Now this is unsorted. This is just directly the list depending on this weights. Okay, so then I have to sort it. So 3, 4, 5, 5, 2, 3, 4, 5, 6 times 6, and 1, 2, 3, 4, 5 times 7. So the median in this case, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So the median is the seventh value, 1, 2, 3, 4, 5, 6, 7, 7 or 8. Eighth value, not the seventh value. So because there are 15 numbers in this list, the median would be the eighth value. So 7 on each side and eighth number being exactly in the middle. So the result of this would be 6. Now, most of the times, the result of a smoothing operation may come as the same value as the current value in your output image also. Okay, so it is not like always this will be the case. If there is something like the salt and pepper noise, as I had shown earlier in this, so in such a case, the output will be like this. That is, it removes the salt and pepper noise, and depending on the surrounding areas, it calculates the value. Now, you will lose some data in this, that is, edges are lost, but it does remove all the noise. So you basically have to find out a balance between removing the noise and preserving the edges. Now, in the frequency domain, the same operation holds, but there is a slight change. If you remember the Fourier transform I told you all, the low frequency data corresponds to slowly changing information. If I go from, let's say, one pixel to another, as I traverse these pixels, if the intensity values are changing slowly, that is, there's no much change across the intensity values, then it is considered as low frequency. And if there is any edges, like if there's a sharp change in the intensity value, then those correspond to the high frequency. So in your image smoothing, what we want to do is we want to preserve these low frequency components. We want to stop the high frequency components. Okay, so what we want to do is we have something called as an ideal low pass filter. Now, the problem with ideal low pass filter, it basically just allows whatever is having a low frequency less than this threshold D0, it allows that to pass. Anything greater than this threshold, it will just stop that. Okay. Now, the problem with this ideal low pass filter is if you see this particular image, ignore the black and white spots. Just pay attention to this line, the edge of the penguin with the background. And after smoothing, if you can see these additional lines which are coming. Now, earlier, if you just ignore the noise, this part had no lines as such. It was just the background with the occasional spots. Okay. Due to this ideal low pass filters frequency response. Now you can read online about why exactly it does this. It is because it has to do with your details in terms of interference or something like that is there. Okay. The problem arises at this point, at this frequency, whether to allow it or to stop it. Okay, that is the reason why you get these additional lines, which are basically following the curve. So if you look at this particular line over here, this is very much the same curve as this penguin's boundary. Okay, same thing comes over here, that this beak that is there, that is what is copied over here. Same thing, this beak creates this line over here. Okay, same thing in the back, and from the head itself till the back of this penguin on the right hand side, you can see the lines coming out at this point. There is a line here, there is a line here, here, and so on. Okay, so this is basically the effect which is caused by using ideal low pass filter, because of the way in which it handles the frequencies near this threshold level. Okay, so to avoid that problem, what we do is we use trapezoidal low pass filter. Now, okay, I didn't put that graph in this. Now, trapezoidal low pass filter basically has its shape, instead of this sharp drop over here, instead of that, the trapezoidal low pass filter basically has a pass at this point, that is 1, and there is some range. Okay, I should not have drawn that. Okay, just let me draw this again. Okay, let's say this is pass, and here it is the final cutoff. So this is my cutoff frequency. Now there is another threshold over here. So instead of just dropping down as an ideal frequency, here it forms like a trapezium. Okay, so we don't just cut off directly at the threshold. At We basically have two thresholds here. So at one threshold, the value is up till that point, everything up till that point is allowed. As we go near this threshold, it starts reducing. So if this value lies between somewhere here, it may get a value like 0.7. If it is very close over here, it may have 0.2 and something like that. Okay, so this threshold response is given by this. Now this DUV in all these cases over here, these are the distance from the central pixel. So if you remember, just a minute, I'll show you all. If you remember the output of Fourier transform, we had that particular image, correlation, this one. Okay, so that distance is basically how far that point is from this central point. Okay, this central point over here correspond, if you can see over here, this white dot in this entire image. The central point corresponds to DC, that is zero frequency. Okay, and as we go away from the central point, we are basically corresponding to higher and higher frequencies. So in a image, if we are applying low pass filtering, we will basically have this distance determining whether we are allowing those frequencies to pass or not. That is what DUV is. The distance from a current point, let's say this current point is somewhere here. So how far it is from this 0,0, that will determine your DUV. Okay. Now, so that is your DUV, and D1 and D0, these becomes your free threshold. So this will be D1 and the other one will be D0. Any questions until now? Yes, students, any questions? Okay, so the last one, which is your Butterworth low pass filter. Now that has a graph something like this. Instead of your straight line between the two cutoff frequencies, we have something like a curve. So we don't basically get it like a straight line, and we just have one cutoff frequency. So if that was your trapezoidal filter, in your Butterworth filter, you will basically get something like this. So if I have this as the value, I'll have this as my pass, whatever the band pass. So all these frequencies less than this cutoff frequency will be allowed to pass. Anything more than this cutoff, not somewhere here. Anything more than this cutoff, as we go away from this cutoff frequency, the value is going to reduce. So something like this, it will come. So as we go away, it keeps on reducing. It does not become zero. It goes very close to zero. Okay. And the equation for your Butterworth filter is given by 1 divided by 1 plus just a minute. I'll have to write it again because there's a power associated with this denominator. I can't shift it from there. So the response h u comma v is 1 upon 1 plus t uv, which is the distance, the current input frequency that we are considering, t0 being the cutoff frequency, and this raised to 2n. So this is the response that it generates if it is beyond this cutoff frequency d0. And if I have, let's say, different values of n, I will get something like this. So this response will change, and how fast it reaches zero, that will depend on the value of n. So you may even have another something like this. Okay, so this n value is going to determine whether it is a steeper drop or not. So as we increase the value of n, it is going to be much steeper. So this blue value will correspond to n1, let's say. Red corresponds to n2. So n1 will be less than n2, less than n3. So this is n1, red n2, and this green n3. So as n3 increases, the drop, the rate at which the value drops, that increases. So we have a much steeper drop in your Butterworth filter for the greater values of n. Any questions with filtering? Numericals will be solving in class. Then we have image enhancement, which is basically our image sharpening. So if we have something like this as the input, we try to get which are the edges in that image. Okay, so that will be your image enhancement. That is, we have three different convolution kernels: Roberts, Prewitt, and Sobel. And we also have something called as the Laplacian filter, which is the same as the output is the same. That is, it calculates the edges. And then we have frequency base. So in that also we have three. That is ideal high pass filtering, trapezoidal filtering, and Butterworth filtering. Any questions with what was covered today? This image enhancement I'll cover later in the next lecture. Up till frequency domain methods for image smoothing. Any questions? Okay, then that's it for today. You all can leave. Thank you.